Have you ever looked up at the night sky and wondered what those twinkling lights really are? They're not just tiny diamonds scattered on a black velvet cloth. They are massive fiery balls of gas, each with its own incredible story. Today, we're going on an epic journey across the cosmos to witness the birth, life, and spectacular death of stars. So, where do stars come from? It all begins in what are called stellar nurseries. These are vast, cold, dark clouds of gas and dust, mostly hydrogen, floating in space. They're absolutely enormous, light years across. Imagine something so big it makes our entire solar system look like a single grain of sand. Now, within these giant clouds, things aren't perfectly still. There are slight variations in density. Gravity, the universe's ultimate architect, starts to pull the denser regions of gas and dust together. As these clumps grow, their gravitational pull gets stronger and stronger, attracting even more material. It's like a cosmic snowball effect. This collapsing clump is called a protostar, a baby star. As the protostar collapses, the pressure and temperature at its core skyrocket. Think about squeezing a bicycle pump. It gets hot, right? Now imagine that on a scale of millions of degrees. The core gets so incredibly hot and dense that something amazing happens. Nuclear fusion ignites. This is the moment a star is truly born. What is nuclear fusion? It's the process where hydrogen atoms are forced together under immense pressure to form helium. This reaction releases an enormous amount of energy. This outward push of energy perfectly balances the inward pull of gravity. This balance is what allows a star to remain stable and shine brightly for billions of years. Our own sun is in this phase, known as the main sequence. It's been happily fusing hydrogen for about 4.5 billion years. And has about 5 billion more to go. The life of a star is all about this battle between gravity trying to crush it and the energy from fusion pushing outwards. But what happens when the fuel starts to run out? Just like a car, a star can't run on an empty tank. A star's fate depends entirely on its mass. Let's start with stars like our Sun, what we call low-mass stars. When a Sun-like star exhausts the hydrogen in its core, fusion stops. Gravity, which never takes a break, starts to win. The core begins to contract and heat up even more. This extra heat causes the outer layers of the star to expand dramatically. The star swells up into a red giant, becoming hundreds of times larger than its original size. If this happened to our Sun, it would swallow Mercury, Venus, and possibly even Earth. Inside the red giant, the core gets hot enough to start a new phase of fusion, this time fusing helium into heavier elements like carbon and oxygen. But helium is a much less efficient fuel than hydrogen, and it runs out relatively quickly. Once the helium is gone, for a star the size of our Sun, that's pretty much the end of the road for fusion. With no more fuel to burn, the star's outer layers drift away into space, creating a beautiful, glowing cloud of gas called a planetary nebula. These aren't related to planets at all. They just looked a bit like them two early astronomers with their small telescopes. What's left behind at the center is the star's hot, dense core, now called a white dwarf. A white dwarf is incredibly dense. Imagine taking the entire mass of our sun and squishing it down into a sphere the size of Earth. A single teaspoon of white dwarf material would weigh as much as an elephant. This white dwarf will simply cool down over trillions of years, eventually becoming a cold, dark black dwarf. A quiet end to a long life. But what about the real giants of the cosmos, the high-mass stars? Stars that are 8, 10, or even 100 times more massive than our sun. Their lives are much shorter and far more dramatic. Because they are so massive, their gravity is much stronger. This means the pressure and temperature in their cores are way higher. They burn through their hydrogen fuel at a furious rate, living for only a few million years, not billions. When a massive star runs out of hydrogen, it also swells up, but it becomes a red supergiant. Betelgeuse in the constellation Orion is a famous example. If you put it where our sun is, it would extend past the orbit of Jupiter. Inside these supergiants, the fusion process goes into overdrive. After helium is used up, the core is massive enough to keep fusing heavier and heavier elements. Carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. And iron is where the story takes a dramatic turn. Fusing elements up to iron releases energy, but fusing iron actually consumes energy. So when the core of the star becomes a solid ball of iron, the energy production suddenly stops. The outward pressure that was holding back gravity vanishes in an instant. What happens next is one of the most violent events in the universe, a supernova. With nothing to support it, the star's core collapses under its own immense gravity. It implodes in less than a second, shrinking from the size of the Earth to a ball just a few miles across. This collapse triggers a cataclysmic rebound explosion. A shock wave rips through the star's outer layers, blasting them into space at incredible speeds. For a brief period, a single supernova can outshine its entire galaxy, releasing more energy than our sun will in its entire lifetime. This explosion forges even heavier elements, like gold, silver, and platinum, and scatters them across the cosmos. Think about that for a second. The iron in your blood, the calcium in your bones, the gold in a wedding ring, all of it was created in the heart of an exploding star billions of years ago. We are literally made of stardust. After the cosmic fireworks of a supernova, what's left behind? Again, it depends on mass. If the original star was massive, but not supermassive, the collapsed core becomes a neutron star. This is one of the most extreme objects in the universe. It's so dense that a sugar cube-sized piece would weigh as much as all of humanity combined. The gravity is so intense that protons and electrons are crushed together to form neutrons, hence the name. Many neutron stars spin incredibly fast, emitting beams of radiation that sweep across space like a lighthouse. If one of these beams happens to point towards Earth, we see it as a pulsar, But what if the original star was even more massive? If the remnant core left after the supernova is more than about 3 times the mass of our Sun, something even stranger happens. Gravity becomes so overwhelmingly powerful that nothing can stop its collapse. Not even the neutrons can withstand the crush. The core collapses forever, shrinking down to an infinitely small point called a singularity. It creates a region of space-time where gravity is so strong that nothing, not even light, can escape. A black hole is born, from gentle stellar nurseries to the quiet fade of a white dwarf, and from the fury of a supernova to the mystery of a black hole. The life cycle of a star is a truly incredible saga. It's a story of creation, destruction, and cosmic recycling that has shaped the universe and made our own existence possible. So the next time you look up at the stars, remember you're not just seeing distant lights. You're seeing the past, present, and future of the cosmos, all playing out in a beautiful, silent ballet. Thanks for joining me on this journey through the stars. If you found this as fascinating as I do, don't forget to like this video and subscribe for more deep dives into the wonders of our universe. See you next time.